It often takes just the right set of conditions between your thoughts and your environment to create the context needed for great revelation to come to light. Even when the evidence is right before our eyes, we can overlook some very important clues if we lack the proper context needed to see the connections in the available information. I believe that when we can disengage ourselves, even for a moment, from any rigid or limiting mindset, then we are open to receiving information that would have otherwise remained hidden or gone unnoticed. I had a revelation in a moment when I was open to new ideas, at a time when the context was just right, and where I'd asked just the right question. My experience came in the form of a vision. I call it a vision because the information was purely visual. However, what this vision revealed to me would change how I saw our Earth, our Moon, and our water forever. It was a cold evening in November of 2007. I was sitting in my backyard and staring up at the full moon, letting my mind drift and dream, as I'm known to do. As I was watching the moon that evening, I was thinking about the amazing and mysterious qualities of a very familiar element to us: water. Water holds unique properties that make it stand out over many other elements. Water is a dipole and acts like a magnet, with the oxygen end having a negative charge and the hydrogen end having a positive charge. These charged ends can attract other water molecules. This is called intermolecular force. Water can dissolve a large variety of chemical substances. Water is sometimes called the universal solvent because it can dissolve almost anything. It can also absorb a large amount of heat, which allows large bodies of water to help moderate the temperature on Earth. Water exists on Earth in all three states: ice, water, and steam. It is densest in its liquid form, at about 4 degrees Celsius. It also expands by 8% when it freezes, making it less dense than liquid water, which is why ice floats. It has a very high boiling point, and when it flashes to steam, it expands a staggering 1,700 times its original volume. These are just a few of water's unique physical and chemical properties. Water is also of vital importance to all of life, and Earth certainly has an extraordinary amount of it. Water covers roughly 71% of the Earth's surface, making our planet very unique amongst all of its neighbors in the solar system. All of the water that exists on our planet today is the same water that has been here since the time of the dinosaurs. This last particular piece of information caught my attention, considering the great abundance of water that's here on Earth. So, eyes still fixed on the full moon, I asked the question, where did all of this water come from? Suddenly in my mind's eye, I'm witnessing a massive ball of ice, about the size of a small planet, hurtling towards an even greater ball of molten rock and iron, our Earth, during the early formation of the solar system. When these great bodies of ice and fire collide, there is a violent reaction. Titanic waves of molten material fan out from the center of the heavy impact. But the icy planetoid does not fully penetrate through the molten ball. The energy of the impact continues through, however, and manages to dislodge a large portion of the mantle on the opposite side of the molten sphere. This is immediately followed by an enormously powerful blast of steam, released when the mantle comes loose. This burst of steam seems to give that dislodged portion of magma the extra push it needs to escape Earth's pull and drift slowly away from that point on as our newly born satellite, our moon. So far, the vision seems to show me an event that brought all or most of our water and created our moon in a single stroke. Yet this is only the beginning. The vision continues. And now, something even more amazing is taking place. Back on Earth, there's a frenzy of activity as the reaction between ice and fire continues to play out. Deep within the molten Earth, the ice is quickly changing into vast oceans of superheated liquid water. Geysers of steam and smoke and fire spew out, whipping up a thick atmosphere and supercooling the topmost layer of the molten Earth into a thin crust. The hot oceans are dissolving many elements within its depths, creating the perfect conditions of heat, water, and nutrients for life to begin to take hold for the first time. The newly born moon even plays its part as the spoon that stirs the primordial soup. Its close proximity to Earth drives massive tides and mixes all the ingredients for life together, accelerating the natural processes of evolution. So now the stage is set. Earth will become the mother she was born to be, as life slowly grows and develops within her oceans, and eventually, when the time is right, onto land and breathing the air of her protective atmosphere. The vision comes to an end. It has answered so much more than my original question, and yet now I have many more. Could this vision truly be how it happened? Now the real work begins. The research, the science, the facts. I want to know. So where to start? In order to do any research, one has to know what they're looking for. Even if I had the means to run a simulation, I would need to know the criteria of the scenario based on the visual information that I received. Let's break down all the visual information to lead us to clues as to where we should look. All of the water on Earth arrived at the same time on a celestial body that impacted the Earth during the early formation of the solar system, henceforth referred to as the impactor. The impactor was spherical in shape and was in a solid frozen state at the time of the impact. The Earth was in a liquid molten state at the time of the impact. The material that primarily makes up the moon is material from the Earth. Steam power played a part in the moon's creation. Steam helped create the atmosphere and cool the outer layer of the Earth into a crust. Life became possible on Earth because of this event. Those are the major criteria of the scenario. Now we might have the information needed to do some calculations and run a simulation. I wish I had the tools to do a simulation. Perhaps someone out there will be able to do this. But I could certainly do some basic math and science. One of the first things I had done was try to determine the mass of the Earth at the time of the impact by adding the mass of the Moon to it. So mass of the Earth without water plus mass of the Moon should give me a good estimate. Determining the size of the impactor, however, might prove more difficult since there could be many factors to consider like mass, material composition, velocity, angle of impact. We do have some clues to work with though. The impactor was spherical in shape, which means there is a minimum mass that it must be depending on what it is composed of. So let's ask, what is the minimum size a celestial body needs to become a sphere?
For a body to become a sphere, it has to have sufficient self-gravity to pull into a spherical shape. This depends on what the body is made of for two reasons. The first reason is because the strength of self-gravity depends on the mass of the object rather than its size, implying that bodies made of denser materials become spherical at smaller radii. The second reason is that some materials are easier to mold into a sphere than others, implying that less strong gravity is needed to push some materials into a spherical shape. The second reason tends to win out. Therefore, for bodies made mainly of rock, the minimum size to become a self-gravitating sphere is about 600 kilometers diameter. But for bodies made mainly of ice, the minimum size is 400 kilometers diameter.
Let's assume for now that the impactor is made purely of water ice, and that its mass is equal to all of the water that exists on Earth today. And we made a great big ball of ice out in space. How big would it be? All of Earth's water would fit into a sphere 1,385 kilometers in diameter, or 860 miles wide. The volume would be 1.386 billion cubic kilometers, or 332.5 million cubic miles, and would weigh 1.383 trillion tons. The size of this ball is just over a third the size of our moon, and the moon is about a quarter the size of the Earth, 27.3% to be exact. Is this enough mass to create the moon? Considering the blast of steam, would that be enough to do it? Is this really all the water on Earth, or could there be more? When I first started doing my research in December of 2007, I wasn't finding much in the way of water being present at the time of the creation of the moon. It seemed that the consensus was that the moon and the Earth at that time were bone dry. Then in July of 2008, an article popped up that seemed to make this scenario much more plausible. Glass beads from moon hint of watery past. Scientists have found water in some tiny beads of volcanic glass that Apollo astronauts collected on the moon decades ago, raising new questions about how the moon was born. For a long time, scientists have thought that the moon is completely dry, said Eric Howry, a geochemist at the Carnegie Institution's Department of Terrestrial Magnetism in Washington, D.C. But Howry got together with some colleagues to look for water in a special kind of material collected on the moon by Apollo astronauts, tiny bits of glass created by volcanic eruptions on the early moon. A study about 10 years ago looked at the beads and saw hints of water, but the results also fell within the instrument's margin of error. So Howry and his colleagues decided to look again, using newer, more sensitive detection technology. But this time they did find water molecules, according to a report in the journal Nature. It wasn't a lot of water. The beads had only up to 46 parts per million. But from this, the researchers estimate that the interior of the moon once probably contained an amount of water equal to that of the Caribbean Sea. This is a problem for the giant impact theory, says Howry. It's hard to imagine a scenario in which a giant impact melts completely the moon and at the same time allows it to hold on to its water. Ever since then, research being done about our moon, our water, and life on Earth has experienced a surge of many recent new discoveries. Now with some new context and perspective, you may see these next videos differently than you might have before.
Scientists have thought for a while now that there may be water trapped within the Earth's mantle. Yeah, a secret ocean underneath our oceans, inside the Earth. This would change our common understanding of what the Earth looks like on the inside. And now there's new evidence that provides even more support for this idea, and that has geoscientists of all kinds wondering how Earth's hidden oceans could have formed. And get this, the new evidence? It's diamonds. Back in 2014, scientists discovered diamonds that contain water-bearing minerals. These diamonds were brought up into human range from deep within the Earth's transition zone, around 640 kilometers below the Earth's surface. So this was pretty remarkable. I mean, how did water get trapped in something that far down? Well, when we're talking about water here, we're not talking about the liquid water that we're familiar with. It's actually the different elements that make up water, hydrogen and oxygen, bound into the crystalline structure of a solid mineral, which is where we get the term water-bearing minerals. See, the Earth's mantle moves by convection, meaning that hot magma rises and pushes other parts of the mantle down further into the Earth. When these water-bearing minerals get pushed down because of this convection activity, the increased pressure literally wrings the water out of them, this time as water we would probably recognize. The initial conjecture that there may be some water deep within the Earth was confirmed by the 2014 diamond discovery, and then backed up with seismic data. The seismic readings were consistent with the idea that there was water in the mantle and that it contributes to the mantle's behavior. But more recently, even more diamonds! These new jewels pulled up from the Earth's depths actually do contain water, but in a totally new form that we've never observed before. These diamonds from several locations across southern Africa and China contain tiny inclusions of a form of water called Ice 7, an extremely high-pressure form of water that scientists refer to as water ice. This is the first time we've ever actually observed this form of water in nature. The researchers say these new diamonds support the presence of at least what they're calling aqueous pockets of water throughout the mantle. So not only is there water definitely inside the Earth, but also it may be in a totally novel form of water that we've never observed in nature before. I feel like that leads us to two important questions. So what? And how did it get there? Well, one answer kind of addresses both. The main theory for how we have water on Earth at all is that it got brought to us by rogue asteroids containing water-bearing minerals crashing into us from the far reaches of our solar system. The theory goes that when the Earth was forming, our solar system was probably too hot for any water molecules to survive and cling to the space dust that would become the Earth. So water had to have been brought to us from off-planet after the Earth formed. But these new diamonds could upend that. Some scientists now estimate that the mantle might contain more water than all of the Earth's surface oceans combined, which is way more water than could have been pulled via convection from the surface of the Earth into the mantle in the given time frame. We may need to re-examine our theories about the state of the solar system at the time the Earth was forming. Maybe it was possible for water to survive and cling to dust and rock as it coalesced to form the Earth. Maybe there's an entirely different theory that we haven't thought of yet. We're still unsure of the exact amount of water in the mantle or what form it might be in. Scientists plan to keep exploring, though, both with seismic measurements and lab experiments that try to simulate the materials and pressures that we would find inside the Earth. And, of course, looking for and examining diamonds. Not the kind that you would put in a ring, but, of course, the kind that contain hydrous minerals, a girl's true best friend. Fun fact, the materials that primarily make up the Earth's mantle are called wadsleyite and ringwoodite, both water-bearing minerals whose structure leaves them prone to gapping, letting researchers think of them a bit like a sponge that's holding the mantle's water. For more awesome Earth science, subscribe to Seeker and check out this video here about the massive asteroid currently headed for Earth. Thanks for watching.
Unlike every other planet in our solar system, Earth's surface is 70% liquid water, which, while useful for life, is also kind of weird, because everything we know about how and when our planet formed says Earth's surface should be bone dry. The story goes like this. Our solar system formed from the collapse of a large cloud of dust and gas. The dense blob of gas at the center ignited to form the sun, which, as a young, unstable star, unleashed a fierce solar wind. Over time, this stream of charged particles pushed the remaining gas cloud farther and farther out, leaving only solid particles behind to clump together into rocks, planetesimals, and finally, the rocky planets of the inner solar system that we know today. And here's the problem. Water, in the form of ice, couldn't have been one of the solid particles that stuck around to form our planet, because the early inner solar system was far too hot for frozen water, and any water vapor would have been blasted away by the solar wind. So if Earth didn't start off with water, how did we end up with such splendid oceans? We know H2O wasn't manufactured here over the eons, because natural processes like combustion, breathing, and photosynthesis create and destroy roughly equal amounts of water. And either way, the amounts in question are so minuscule that they can't account for the abundance of water on the planet. Since Earth's water was neither part of the original package nor manufactured here, it must have flown in from far away, on meteoroids or comets or other bodies originating in the outer solar system where they were far enough from the sun for frozen water to survive. The dirty ice balls we call comets are a logical candidate for the source of our water, but were ruled out when we discovered that they were far richer in heavy hydrogen than Earth water. Heavy hydrogen has a neutron as well as a proton in its nucleus, and for every million hydrogen atoms in Earth water, about 150 are heavy ones, while typical comet water has twice that many. These mismatched chemical signatures suggest that Earth's water couldn't have arrived on comets. It turns out that the most likely source for Earth's water is a type of meteorite called a carbonaceous chondrite. Chondrite is just the name given to the class of stony meteoroids that most commonly strike the Earth. But only the carbonaceous chondrites contain water, as well as lots of carbon if you couldn't tell from their name. They have water in them because they formed out beyond the sun's frost line, and what's more, their water has levels of heavy hydrogen similar to that of Earth water, strongly suggesting that these Earth crashers are the source of our ice caps, clouds, rivers, and oceans. And thus the water that turned our planet into a blue marble came quite literally out of the blue.
Our next experiment embraces one of the most dangerous forces of nature. Almost 4 million people have watched red-hot lava meet ice. We caught up with artist Bobby Saki and geologist Jeff Carson and their rumbling lava furnace to ask them what they thought would happen.
I had no idea what it was going to do. No idea at all.
The first guess is always it's going to explode. Always number one. Or it's going to tunnel down, it's just going to dig right through the ice, melt a hole in the ice. And of course, it didn't do any of those things.
I was stunned by what it did when it hit the ice. And you see the bubbles, bubbles this big, and then there's bubbles within bubbles.
The scrambled eggs from hell is the way it looks in that video. It just did things we just didn't really expect.
So why are volcanic bubbles formed?
The lava is so hot that when it's poured onto the ice instantly turns not just into water, but straight into steam.
Now, this steam has to escape, so it bubbles through the lava. So while it looks like the lava itself is boiling, it's actually the steam being produced that is trying to escape.
As the lava cools, we start to get a thick black layer forming on top, and this starts to trap those bubbles of superheated steam inside the rock, and it's kind of like a natural form of glass blowing.
But how does the lava crawl across the ice? Shouldn't it melt right through?
The formation of all of this steam helps the lava to flow because it means that it's sitting on top of a blanket of steam rather than in contact with the ice itself. And this means the friction between the lava and the ice surface is very low.
Now Bob and Jeff are taking things to the next level. It's lava versus water.
Wow. We've done over 100 pours into water, onto ice, onto sand, onto snow.
We're learning a lot. There are things that are happening here that we had not anticipated. It's beautiful stuff.
Stand back. That sputtering lava's over 2,000 degrees Fahrenheit.
Welcome to the Earth of 4 billion years ago. This was our planet before life. Nobody knows how life got started. Most of the evidence from that time was destroyed by impacts and erosion. Science works on the frontier between knowledge and ignorance, not afraid to admit what we don't know. There's no shame in that. The only shame is to pretend that we have all the answers. Maybe someone watching this will be the first to solve the mystery of how life on Earth began.
The Earth and the Moon were born together, and they have dramatically shaped each other's evolution. Now, we think that life was also given a head start by the presence of our oversized moon. This is the Earth 4.4 billion years ago, around the time scientists think life on Earth got started. The newly formed moon sits just 15,000 miles away, appearing much larger in the sky than it does today. Its gravity raises enormous tides in the Earth's warm, young oceans.
In that era, the tides were not measured in feet, they were measured in miles. you'd have these massive tsunamis that would wash up on land and then wash back into the sea.
The moon's gravity creates tides by drawing Earth's oceans up toward it in a bulge of water. And as the Earth spins, this bulge washes onto land as a tide. The closer the moon, the bigger the pull of gravity, and the stronger the tide. Some scientists think that the warm rock pools, these giant early tides left behind, formed the perfect mixing bowl for the ingredients of life to come together.
The good thing about a tidal pond is that environments change. Water comes in, brings nutrients, goes away, the nutrients concentrate. So that may have been a process that concentrated the stuff life needed in a way that led to life.
$4.4 billion years ago, onrushing tides stir up organic molecules from the surface of the Earth. As the tides recede, these chemicals are left behind in shallow rock pools, which then evaporate in the heat of the sun, concentrating down their chemical contents. Perhaps the first life was born inside this rich, organic soup.
If we had tiny little moons around the Earth like Mars does, then we never would have had the massive tides that carry materials and energy up onto the beach environment where life really might have gotten a foothold. And so we wouldn't have had the minerals, we wouldn't have had the energy, and maybe we wouldn't have had life.
Did the moon create life on Earth? The jury's still out. But one thing's for certain, intelligent life takes time to evolve. In our case, at least 4 billion years. We've gradually changed from simple, single cells to the kind of organism that can question its own origins. And it's the moon that's provided the stability for life to evolve by holding the Earth's axial tilt steady for over 4 billion years.
The origin of life on Earth is complicated, and no one really knows exactly how it began. Nonetheless, there are two main components that we do know needed to happen in order for life to have gotten started. First, there must have been a genetic molecule, something like DNA or RNA, capable of passing along blueprints for making proteins. And second, Earth must have had access to the essential elemental ingredients of life, such as carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. But even if we don't know how life began, we do have some nifty theories. So welcome back to Curiosity 180, and let's talk about it. The most common theory is that life began purely by accident. This theory is called the primordial soup theory, which suggests that life began in a pond or ocean. These soups were filled with amino acids, the building blocks of proteins, which would eventually evolve into the first species on Earth. These molecules would have collided at random for millions of years until the perfect combination just magically happened in order to spark the creation of life. However, the chances of life just spontaneously creating itself doesn't seem likely. Can you imagine how lucky we are if all of this was just an accident? But there is another more intriguing theory called panspermia, which states that life could have originated somewhere else and is being spread from planet to planet by asteroids. The asteroids would have carried genetic material or some component of genetic material. If met with ideal conditions on a new planet, the bacteria would become active and the process of evolution begins. This theory is supported by two main facts. First, we know it is possible for rocks from other planets to reach Earth. In fact, there are rocks from Mars on Earth. Second, we know life can actually survive through space. Tardigrades, a microbe, are notable for being the most durable of known organisms. They are able to survive extreme conditions that would be fatal to nearly all other known life forms. But these are just theories, whether you believe them or not. Life has already started, so enjoy it, and watch more Curiosity 180 videos.
What you're going to see now is a brief animation of A Theory for the Origin of Life, developed by Mike Russell and Bill Martin. The origin of life on Earth to be sought before 3.8 billion years ago because sedimentary rocks of that age contain evidence for life, but after 4.2 billion years ago because geochemists tell us that that's when the first water was stably existing on Earth. Now, we're not going to be looking at warm little ponds of the time that Darwin had in mind because at that time, late heavy bombardment, land was not a pleasant place to be. Things were certainly more stable at the bottom of the ocean. And since their discovery in 1978, people have thought that maybe these black smoker type of hydrothermal vents might be important for the origin of life. Now, we think that a different kind of vent discovered by Deb Kelly and her co-workers in 2000 called Lost City type of vents or off-ridge vents might be more relevant for the origin of life because their chemical conditions are more conducive to life, not quite as hot and maybe a little bit richer in hydrogen. Now, the geochemical differences between these two types of systems are schematically illustrated here. On the right, you can see the black smoker kind of vent with the sitting directly above a magma chamber. Now, that magma is 1,200 degrees, and that's why the water coming out of black smokers is about 350 degrees. That's, we think, too hot for the origin of life. On the left, you can see the Lost City kind of vent, and there we think that this the water coming out of the Lost City kind of vent is much cooler, around 70 to 90 degrees, and we think a very important process going on that's been characterized at Lost City called serpentinization is going to be important for the origin of life. That's schematically represented here. We've got water molecules being reduced by inexhaustible reserves of iron-2 in the Earth's crust to molecular hydrogen that leaves the vent in the effluent as these little white balls along with sulfur shown in yellow. Now, at the vent-ocean interface, the sulfur precipitates iron-2 and nickel, shown here in black and green, to give us transition metal sulfides. These mineral precipitates will have two very important functions, catalytic and compartmentalization. Their catalytic ability is going to be shown in the next blend in here. And transition metal sulfides have long been known to have very important catalytic abilities in organic chemistry. Here, hydrogen-dependent reduction of carbon dioxide to carbon monoxide, similar to what we see today in an enzyme called carbon monoxide dehydrogenase, maybe being connected up via methyl groups or methyl sulfide to acetyl thioesters, which we think are very important compounds. The most central compound in all of metabolism is an acetyl thioester, acetyl-CoA, and we think that that has a reason. Now, the compartmentalization function is shown here. These little green dots are RNA precursors and amino acids here polymerizing into RNA-like molecules to give us the RNA world, and little peptides floating around there, but not genetically encoded ones. For that, you need the ribosome and the genetic code, and that we have right here. Every other theory for the origin of life has to solve this problem. We solve it here, but within these self-forming inorganic compartments, the contents of which then give rise to the common ancestors of the eubacteria and the archaea bacteria, which we think were acetogens and methanogens respectively. They make the transition to the free-living state, divide and populate the Earth, and its Darwinian evolution among prokaryotes since then.
This deep thought experiment was meant to introduce the scenario of a prehistoric event that brought our water, created our moon, and initiated life on Earth. By looking at this scenario through the scientific data and research that we currently have available, we can see that it is plausible. However, we are just scratching the surface. In the next episode, we will dive even deeper into this mystery to see if we can discover more clues about this prehistoric puzzle. Thank you for watching. We are all together on this journey of discovery. Join the discussion and leave your comment below. Please like, share, and subscribe to be updated on more content from this channel. Thanks again, and take care, everybody.